last talk of this season. Our next speaker is Dr. Sorry, uh, Dr. David Albert. Professor David Albert is professor of philosophy and director of the MA program in the Philosophical Foundations of Physics at Columbia University in New York. His research includes subjects such as philosophical problems of modern physics, philosophy of science, philosophy of quantum mechanics, and the philosophy of space and time. Professor Albert has published three books, including Quantum Mechanics and Experience, Time and Chance, and After Physics, as well as numerous articles on quantum mechanics. Today, Professor Albert will be talking about the direction of time from the cosmos to local systems. It is an honor that you accepted our invitation, Dr. Albert, and we are looking forward to your talk. You can start your presentation. We have a 45 minutes talk followed by about 15 minutes for question and answer section.
Wonderful. Can you hear me?
Yeah.
I seem to be having trouble turning on my camera. I'm not sure why. When I click on my camera, I get a message that says browser is not allowed to access the webcam.
Okay.
But I'm using the Chrome browser.
I think our technical team can resolve your problem.
Oh, thank you so much.
Professor Albert, I think you should click on an icon on the toolbar on top of your page and get and let the permission to your camera let the permission to browser to use your camera.
Yes, I did do that. Let's see. I'm going to click on the camera icon again. I did do that before, and when I gave them permission, I get an icon that says I get a message that says browser is not allowed to access the webcam.
You can try exit the room and enter again. Maybe it can fix it.
Okay, I will try to enter again. Then I will exit. Good. I will just close this tab then, and then enter the room again.
No, click on the three lines icon and press exit.
Oh, okay.
Okay, and come again.
Right. So I press.
Hmm?
Can you hear me?
Yes, we
Yes.
can hear you.
Okay, now should I click on the camera icon again?
Yes, please click on it.
Okay. I still get browser is not allowed access to the webcam.
Let me see.
I'm so sorry.
No, it's not a problem. Okay. Let me see. Okay. Could you go to the settings of your browser?
The settings of my browser.
Yes, into the privacy section.
Hold on a second. You mean preferences?
Settings, privacy, and security.
Hold on a second.
Okay.
Settings, privacy, and security. Yes.
Yes. Okay. Site settings.
Site settings. see privacy guide. I don't see something. Oh, hold on. Safety check, safety and security. Site settings. Yes.
Yes.
I'm
In
sorry.
there, you can get the permission to access your camera.
Yes. Okay. Allowed camera and 2 more. Right. Good. Okay. So now I should go back.
You should, yes, yes. Now your camera must work.
Okay. Hold on. Gosh, no. I'm getting the same. Should I re-enter the room?
We can try that again.
Okay, I'll try. I'm so sorry for this.
No, it's okay. There's no problem. چرا نشد واقعا باز؟
Okay, I'm back in. I will try the camera icon again. No, I'm getting the same message. I can, of course, deliver the talk without an image of me. The way I look is not so important.
Okay, if you
Yes, I can.
it's not okay. If it's not
We can
important,
continue this way.
Okay, I'm so sorry.
No problem.
Good. So shall I begin now?
Yes, Professor Albert, do you see the 3 dots icon over your slides?
Yes, I do.
Click on that and click on Take Ownership so you can control your slides.
I see. Okay.
Thank you. You can start your presentations.
So in this way, I see I can go forwards and backwards. Okay. Thank you so much. Well, I'm sorry not to be appearing before you visually, but I'm very pleased and invited to have been asked to this meeting, and I very much appreciate the chance to talk to you. Our everyday macroscopic experience of being in the world is saturated with asymmetries, thermodynamic asymmetries and radiative asymmetries and epistemic asymmetries and phenomenological asymmetries and asymmetries of overdetermination and asymmetries of influence and what have you between the past and future. And there is a long cherished hope, something that has its origins in the work of Boltzmann and which has been pursued by any number of other investigators through any number of fits and starts and revelations and wrong turns ever since, a hope that all these asymmetries can ultimately be traced back to some relatively simple characteristic of the initial macro condition of the universe. The thought, as people put it nowadays, is that all we need to do in order to account for these asymmetries is to add to the fundamental time reversal symmetric dynamical laws and to the standard statistical mechanical probability measure over the space of possible fundamental physical states, a simple postulate, a so-called past hypothesis, to the effect that the world first came into being in whatever particular low entropy macro condition it is that the normal inferential procedures of cosmology are eventually going to present to us. The business of working this thought out in detail is a large undertaking, which is still very much in its infancy and which is still the topic of very lively debate. And I don't want to attempt anything along the lines of an overview of that project here. All I want to talk about today is a widespread and fundamental and perennial sort of puzzlement about how it is that such a project could even seriously be entertained. A puzzlement, that is, about how it is that the macro condition of the universe 15 billion years ago, all by itself, could even imaginably be up to the job of explaining so much about the feel today and on Earth of the passing of time. The puzzlement takes a number of different forms and arises in a number of different contexts. On the most trivial level, there's a question of how the lowness of the entropy of the world 15 billion years ago can impose any genuinely profound and vivid constraints, whatever, on what the world is doing now. And all that needs to be said in order to make that sort of puzzlement go away is that although 15 billion years is a long time, the entropy of the universe at that time was very, very low. And that in particular, 15 billion years is a great deal shorter than the expected relaxation time of the state in which our universe seems to have started out. But there's a somewhat more interesting question in the general vicinity of this first one about how the lowness of the entropy of the world 15 billion years ago can have any genuinely profound and vivid effects or impose any genuinely profound and vivid constraints on what particular localized human scale quasi-isolated subsystems of the world are doing now. There's a worry, in particular, that runs like this. Let it be stipulated that the standard Boltzmannian arguments do indeed establish that the overall entropy of the universe, which starts out in a low entropy past hypothesis sort of macro state, is overwhelmingly likely to increase toward the future. People are fond of pointing out that that tells us nothing at all in and of itself, and considered as a purely logical matter, about the behaviors of the entropies of quasi-isolated subsystems of the world. Just as the fact that dogs can run tells us nothing at all in and of itself, and considered as a purely logical matter, about whether or not dogs' heads can run. And it is the behaviors of quasi-isolated subsystems of the world, after all, and not of the universe as a whole, that the science of thermodynamics is primarily, and in the first instance, about. And all of this, considered as a purely logical matter, is surely true. But it seems to me to ignore, or to overlook, or to misunderstand how the Boltzmannian arguments actually work. The core of what the Boltzmannian tradition has given us is a general strategy for assigning specific numerical probabilities to any propositions whatever about the microconditions of isolated thermodynamic systems at any time t greater than t0, given the macro condition of the system at t0. And the argument to the effect that thermodynamic systems in non-equilibrium macro conditions are overwhelmingly likely to increase their entropies as time goes forwards is simply an application of that general strategy to the special case of entropy. The business of actually calculating those probabilities in physically interesting cases is usually going to be prohibitively complicated. But what Boltzmann and his various collaborators and inheritors are widely thought to have made plausible is that those probabilities are in good accord with the entirety of our everyday thermodynamic experience. If, for example, the isolated system in question consists of two gases which are initially at different temperatures and which are in thermal contact with one another, what the Boltzmannian arguments make plausible is not merely that the overall entropy of the system is overwhelmingly likely to go up toward the future, but in addition, that the entropy of the hotter gas is overwhelmingly likely to go down toward the future. And if the isolated system in question consists, say, of 12 isolated gases in 12 separate containers, each of which is initially far from its own individual equilibrium state, then what the Boltzmannian arguments are going to make plausible is not merely that the overall entropy of this system is overwhelmingly likely to go up towards the future, but in addition, that the separate entropies of each of those 12 gases are all individually overwhelmingly likely to go up toward the future. Of course, the probability that the entropy of some particular one of those gases goes down toward the future will be much higher than the probability of the overall entropy of the 12 of them together goes down toward the future. But both of those probabilities are going to be fantastically small. And there's also a third question in the general vicinity of these first two, which is the deepest and the most interesting and the most amorphous and the most phenomenological form of the general puzzlement about the Boltzmannian project that I mentioned at the outset of my talk. And it's that third question that I mainly want to talk about today. Let me put this question in four increasingly concrete and increasingly simple and increasingly tractable ways. One, how can it seriously be imagined that my own sense of the passage of time, how can it seriously be imagined, for example, that my own sense right here and right now of whether some particular baseball happens to be flying towards me or away from me is somehow anchored in the lowness of the entropy of the universe 15 billion years ago? Two, how can it be, how can it work that the increase of the entropy of the world or of myself somehow constitutes the standard or the yardstick against which I judge the direction in which events are unfolding? How is it, that is, that the entropy gradient of anything ever comes into the picture? I'm certainly not aware of checking on the entropy gradient of anything in the course of deciding whether the baseball is flying towards me or away from me. No comparison with anything else, so far as I am aware, is involved. I simply, directly, unmediatedly see that the baseball is flying either towards me or away from me. Consider the sense, third way of formulating the question. Consider the sense of the direction of time that is implicit in the operations of, for example, a simple mechanical realization of a Turing machine. Can anyone seriously believe that thermodynamical characteristics of the world somehow play a role in the way that a machine like that distinguishes between what it has just done and what it is supposed to do next? How so? How can that be? How would that work? Machines like that can apparently function perfectly well. Machines like that can apparently have no trouble at all in distinguishing between what they have just done and what they're supposed to do next, without the aid of special devices for measuring the entropy gradient of the world or of themselves or of anything else. Consider, finally, and here is the fourth version of the question, and the most tractable version of the question. Consider, finally, a simple mechanical device which has no other business than distinguishing between what it has just done and what it is to do next, what it is supposed to do next. The paradigmatic distinguisher, the distinguisher, you might say, par excellence, between what it has just done and what it's supposed to do next. Think, that is, of a clock. And think, for the sake of concreteness, for the sake of simplicity, of an old-fashioned, fully mechanical pendulum clock. Good. Now we have our hands on something that we're in a position to analyze in detail. Note, to begin with, that in the course of the normal and intended operations of a clock like this, there are going to be moments, the moments in particular when the pendulum is precisely at the apogee of its swing, when the pendulum is at the highest point of its swing, when every last one of its macroscopic moving parts is completely at rest. Note, to put it slightly differently, that in the course of the normal and intended operations of a clock like that, there are going to be moments, the moments again when the pendulum is precisely at the apogee of its swing, when the macro condition of the clock in its entirety is invariant under time reversal. And consider how it is at moments like that the clock manages to distinguish between what it has just done and what it's supposed to do next. The macro condition of the clock, together with the microscopic dynamical equations of motion, together with the statistical postulate, is manifestly not going to do the trick. For if the present macro condition of the clock, together with the microscopic dynamical equations of motion and the statistical postulate, makes it likely that the clock is going to read, say, 3:05, 5 minutes from now, and if the present macro condition of the clock is invariant under time reversal, then the present macro condition of the clock, together with the microscopic dynamical equations of motion and the statistical postulate, both of which are invariant under time reversal as well, is necessarily also going to make it likely, and to exactly the same degree, that the clock will read 3:05, that the clock read 3:05 5 minutes ago. And all there is to break the symmetry, all there is that stands in the way of the clock's having read 3:05 5 minutes ago, is the past hypothesis. The clock's ability to distinguish between what it did last and what it does next, and your ability to distinguish between a baseball's flying towards you and a baseball's flying away from you, is anchored in the entropy gradient of the universe. If we were to hold the present macro condition of the world fixed and move the past hypothesis from the beginning of time to its end, the clock would run backwards. Period. Case closed. End of story. But the fact is that people sometimes find this hard to take in. Here, for example, is the reaction of an anonymous referee. And this, by the way, is someone I have reasons to believe is a well-known theoretical physicist. Here's the reaction of this anonymous referee to an earlier version of this paper. And I will put this up so people can follow it, because we'll look at it in detail. I'll read it out. It's uncharacteristic of Albert to pass over the details. He could have described how a pendulum clock works, e.g. falling weight version, in a couple of minutes, but he didn't. The mechanism cannot run backwards. What drives it is the falling of the weight, pulling on the cord. If there's no pull on the cord, the clock stops. If there's push on the cord, the clock stops. It'll only work if there's tension in the cord, and that will make the hands move clockwise because of the way that the cord is wound around the drive axle. And that would be true even if the weight rose into the air and started pulling upwards. Putting the low entropy in the future of the universe can't make the clock run backwards, as he claims. The clock, quote, knows which way to go, if it's going to go at all, because the information is built into the way that the cord is wound around the axle. And this will be worth pausing over, I think, and thinking carefully about. Let me begin by simply reiterating the very general point that I made a minute ago. The referee must somehow be mistaken. No further details about the inner workings of the clock can make the slightest bit of difference here. Consider again a moment when the macroscopic state of the clock is stationary. Consider that is a moment when the macroscopic state of the clock is invariant under a reversal of all of the velocities of its microscopic particulate constituents. In the absence of a past hypothesis, the predictions of statistical mechanics about the evolution of the macroscopic condition of this clock away from that moment toward the future are going to be identical to its predictions about the evolution of its macroscopic condition away from that moment towards the past, for the simple reason that there is nothing whatever in the situation to distinguish between them. In the absence of a past hypothesis, the predictions of statistical mechanics are, in particular, that as we proceed away from the present in either direction, the cord is always going to be unwinding, and the weight is always going to be going down, and the hands of the clock are always going to be turning in the clockwise direction. And it is only because of the truth of the past hypothesis, it can only be because of the truth of the past hypothesis, that as a matter of actual fact, those hands turn counterclockwise as we proceed away from the present in the direction of the past. And that, again, is why a clock like this can be used, just as we might use a half dispersed puff of smoke or a half melted block of ice as an indicator of the temporal direction in which the entropy of the universe as a whole is increasing. Good. But there is a puzzle here. Consider a half dispersed puff of brightly colored smoke in an otherwise empty, transparent cubical container. The entropy of this puff of smoke is going to be a relatively simple, monotonically increasing function of its volume. So we can determine the temporal direction in which the entropy of this puff of smoke is increasing by simply noting the temporal direction in which its volume is increasing. And what that means, since the temporal direction in which the entropy of this puff of smoke is increasing is overwhelmingly likely to coincide with the temporal direction in which the entropy of the universe as a whole is increasing, is that we can determine the temporal direction in which the entropy of the world as a whole is increasing by noting the temporal direction in which the volume of this puff of smoke is increasing. You might say that the puff of smoke wears its entropy, and by extension, the entropy of the world as a whole, on its sleeve or on its face. And look at how differently everything is. Look at how utterly different everything is with the clock. We determine the temporal direction in which the entropy of the world as a whole is increasing, or at any rate, we are convinced that we can determine the temporal direction in which the entropy of the world as a whole is increasing by noting the temporal direction in which the hands of the clock are moving clockwise. But how does that work? The entropy of the puff of smoke, remember, is a relatively simple and monotonically increasing function of its volume. But the entropy of the clock is no function at all of the positions of its hands. And the reason that we can determine the temporal direction in which the entropy of the world is increasing by noting anything at all about the smoke is that the smoke is in thermodynamic disequilibrium. The reason that we can determine the temporal direction in which the entropy of the world is increasing by noting anything at all about the smoke is that the smoke is undergoing a process of dissipation. But clockmakers invariably go to a great deal of trouble precisely in order to eliminate any potential sources of dissipation, any rubbing or scratching or denting or heating or what have you, from the clocks that they produce. And if I open up a pendulum clock and examine its inner workings, I find nothing that looks as if it's been designed to measure the volume or the temperature or the pressure of anything. I find nothing, that is, that looks as if it's been designed to track some process of thermodynamic equilibration. So what's going on here? How does the increase in the entropy of the world or of the clock or of anything at all even get into the picture here? How does anything, how does any of that ever become relevant to the direction in which the clock hands are turning? That's the puzzle. And that, I think, is what has the referee so confused. And it is indeed, on the face of it, confusing. Let's have a look then. Let's have a look then at the inner workings of the sort of pendulum clock that the referee has in mind. And I've drawn a very crude picture of that here. I hope it's understandable. I'll explain the details. Note that the cord to which the weight is attached is wound around the axle in a clockwise direction, so that the axle itself and the clock hands that are attached to it rotate in the clockwise direction as the weight descends. The rest of the mechanism, the pendulum and the escapement mechanism, are apparently simply there in order to regulate the rate at which the axle rotates. If they weren't there, the axle and the clock hands that are attached to it would rotate more and more quickly as the weight accelerated under the influence of gravitation towards the floor. What the pendulum and the escapement do is to set a limit, call it theta, on the angle through which the axle is able to turn over the course of any single swing of the pendulum. What happens in a little more detail is this. We begin in the macro state depicted in this picture. The pendulum is at the height of its rightward swing. It's at the apogee of its rightward swing. And as it begins to swing towards the left, the little red metal tab on the left is lifted out of the way of gear tooth number 1, which I hope you can see indicated there. And the weight is able to exert an uncanceled torque on the axle, pulling it in the clockwise direction. As the pendulum swings toward the left, the little red metal tab on the right is lowered into the path of gear tooth number 2. And the ensuing collision stops the rotation of the axle dead in its tracks, where it is held fast by the pressure of the weight until the pendulum begins to swing back towards the right. As the pendulum swings toward the right, the little red metal tab on the left is lowered into the path of gear tooth number 3. And the ensuing collision stops the rotation of the axle dead in its tracks, where it's held fast by the pressure of the weight, and the process then begins again. And what the referee seems to have overlooked, and this is the heart of the matter, is that all of this critically depends on the occurrence at every swing of the pendulum of phenomena like denting and scraping and heating in the operations of the escapement. For suppose that no such things, no denting or scraping or heating ever did occur. Suppose in particular that the collisions between the gear tooths and the little red metal things were perfectly elastic collisions. We begin again with the macro state depicted in the picture. The pendulum is at the height of its rightward swing, the highest point. As it begins to swing towards the left, the little red metal tab on the left is lifted out of the way of gear tooth number 1, and the weight is able to exert an uncanceled torque on the axle, pulling it in the clockwise direction. As the pendulum swings toward the left, the little red metal tab on the right is lowered into the path of gear tooth number 2, and in the ensuing elastic collision, the clock tooth will bounce off the metal tab, and the axle will completely retrace its previous clockwise rotation in the counterclockwise direction, at the end of which the little red metal tab on the left will be smoothly reunited in exactly the configuration shown in the picture with clock tooth number 1. And then, of course, the whole process will simply begin again, and the axle will turn clockwise by theta, and then counterclockwise by theta, and then clockwise by theta, and then counterclockwise by theta, and so on forever. The clock will be rendered utterly incapable of distinguishing between the past and the future. Good. Let's take one more look then, with all that in mind, at the words of the anonymous referee. The referee says, putting the low entropy in the future of the universe can't make the clock run backwards, as he, that is me, claims. The clock knows which way to go, if it's going to go at all, because the information is built into the way that the cord is wound around the axle. Well, let's see. Something is plainly right to begin with about the referee's claim that the clock knows which way to go, if it's going to go at all, because of the information that is built into the way that the cord is wound around the axle. If the cord were wound around the axle in the opposite direction, after all, the axle would plainly turn in the opposite direction. But with respect to what? With respect to the temporal direction that we have arbitrarily and as a matter of pure convention labeled with a plus sign? Of course not. How could that be? With respect to the temporal direction that's picked out by some fundamental metaphysical arrow of time, which makes no appearance whatever in the laws of physics? How could that be? What must be the case, and what we ought to have seen all along, and what we've just now managed to spell out in full mechanical detail, is that the information that is built into the way that the cord is wound around the axle is information about which way to turn with respect to the entropy gradient of the escapement mechanism. What must be the case, and what we ought to have seen all along, and what we have just now managed to spell out in full mechanical detail, is that the information that is built into the way that the cord is wound around the axle is information about the way in which it is information about which way to turn with respect to the temporal direction that points away from the Big Bang, away from the past hypothesis. And we can now see, in particular, that in the absence of dissipation, and notwithstanding the particular way that the cord happens to be wound around the axle, a clock like this is going to have no clue which way to turn. We can now see, to put it slightly differently, that in the absence of dissipation, and notwithstanding the particular way that the cord happens to be wound around the axle, the macroscopic evolution of a clock like this, not merely the laws of that evolution, mind you, but the evolution itself, is going to be completely invariant under time reversal. Suppose, for example, that we are shown a movie of the operations of a clock like the one we have just now been talking about, turning clockwise by theta, and then counterclockwise by theta, and then clockwise by theta, and so on ad infinitum. Nothing about the sequence of images with which we are presented, and nothing in particular about the way the cord happens to be wound around the axle, is going to tell us anything at all about whether the movie is being run forwards or in reverse. So, it's perfectly true that clockmakers take great pains to eliminate every imaginable source of dissipation from the mechanisms they produce, and they are perfectly right to do so. But it is also true, and it is a beautiful and ironical and surprising feature of the way that the world actually turns out to work, that if these clockmakers were ever to perfectly succeed, their clocks would be perfectly useless. And to make a long story short, I suspect that something very much along these lines must explain how a typical mechanical realization of a Turing machine knows the difference between what it did last and what it does next. And it seems to me that once all this has been taken on board, the atmosphere of mystery around my own ability to sense the difference between a baseball flying towards me and a baseball flying away from me, to sense it, mind you, immediately and without any conscious act of inference, and without my ever being aware of checking on the entropy of anything. It seems to me that in light of these considerations, the cloud of mystery surrounding all of that entirely melts away. Thank you very much. And I'm so sorry again, not to have been able to show my face. I've tried to compensate in my voice for the hand gestures that I would usually use in explaining myself. So I hope this has been a little bit understandable. Can anyone can people hear me?
Thank you very much, Professor Albert. Brief slides with deep insights. Now we have question and answer section.
Wonderful.
Yeah. Some of our audiences write their questions in the dialog box. Otherwise, we can hear your voice, dear audiences. If you have any questions, please raise your hand.
Yes, and if people wrote them, can the people who wrote them in dialog boxes also speak them, or is that not possible?
No, it's not possible. They prefer to write. They prefer to write here their questions.
I see. So let me take a look in the dialog box.
Okay. Okay.
Let me see. Right.
Have we any questions? Yeah.
So I'm just scrolling the dialog box. Most of what I see so far. Okay. Here's a question.
Yes.
What would be the nature of the proposed superluminal signal? Oh, I think this must be for the previous talk.
Yes.
Yes, sorry.
Okay. I will read. Was the first state of the universe law in entropy or just law entropy with respect to us?
Let's see. I guess I need to hear a little bit more about the question. I mean, yeah, it needs to be, what's crucial is that the entropy of the initial state of the universe has to be much, much, much lower than the present entropy of the universe. That is, for example, as I was saying in the beginning, it has to be low enough so that the 16 billion years that we think the universe has been in existence is a time much, much shorter than the relaxation time to equilibrium of a state like that. So there is an absolute sense in which it has to be low. It has to be low enough so that it would have taken it 16 billion years to relax to a state like this one.
Thank you. The other question, are time and entropy two sides of the same coin? If not, which one is more fundamental?
So that's a good question. I guess I think that they're not quite two sides of the same coin. That it's a deeper part of the metaphysical structure of the world, than in addition to the three spatial dimensions, there's a temporal dimension. I think, like the three spatial dimensions, that temporal dimension doesn't come with any fundamental direction attached to it. I'm sorry, there's a siren out my window here. but it should pass in a minute. So that fundamental time parameter doesn't come with any direction attached to it. I think the directedness of time that we sense in our everyday lives is a phenomenon that we encounter a little farther up when we come to the basic physical laws. That is, when we come to the thermodynamic behavior of the world. So I guess I would say, no, they're not two sides of the same coin. One of them is lying at a more fundamental metaphysical level, and it's time rather than entropy that's lying at the more fundamental physical level.
Okay. The next question.
Can you hear my voice?
Yes.
Yes.
Okay, so my question about was the state of the universe in first place low in entropy or not? I read something about how entropy is just how much information do we have from the state of a system.
Mm-hmm.
So what my question was about was that if the universe, with respect to what
Good.
system was it low?
Good. Now I understand the question much better. Thank you for clarifying. So look, there is an important connection. There are all sorts of important connections between notions of entropy and notions of information. But I think it's a big mistake to talk, as some people do, about entropy itself as a somehow epistemic notion, as a question of how much some epistemic agent knows about the system in question. Now I understand what you were asking about much better. I'm sorry for my misunderstanding before. I think what we're doing in statistical mechanics is trying to understand thermodynamic entropy. Okay, thermodynamic entropy, is given by delta Q over T. Over the course of some thermodynamic transition, it's an objective property, an objective physical property of a macroscopic object. The object would have that property completely irrespective of what anybody knows or doesn't know about that object. And it would have that thermodynamic property even if there were no conscious agents, even if there were no epistemic agents anywhere in the world. This is the way that Boltzmann tries to understand the entropy. Boltzmann makes this great discovery that this thing that corresponds to thermodynamic entropy is proportional to the logarithm of the number of different microscopic ways there are of realizing this particular macrostate. And so it's true. It's a true statement that in light of Boltzmann's discovery, the information that a system is in a very low entropy macrostate gives us more information about its microstate than the information that it's in a higher entropy macrostate. That more can be determined about the microstate of a system from a report that its macro entropy is low than can be determined from a report that its macro entropy is high. So there is this kind of relationship between entropy and information, but some people, it seems to me, have misunderstood this kind of talk and spoken as if what we mean by the entropy of a system, is some kind of a measure of what we happen to know about it at a given time. And that seems to me a big mistake. And if you go that way, you're going to have no hope of recovering stuff like the laws of thermodynamics from statistical mechanics, because we presume the laws of thermodynamics are just perfectly objective laws about how systems behave, whether there are any knowers in the universe or not. So again, I now understand what you meant when you asked, "Is it relative to us?" No, entropy is something that exists quite independently of the activities of any observers. Okay, and I'm thinking here of a Boltzmannian picture of entropy, as opposed to what's sometimes called a Gibbsian picture of entropy, which does sometimes suggest to people that entropy is some measure of how much we happen to know about the system. I think that's a confusing way to talk.
Okay, thank you very much. Halatai has raised his hand for a long time. Can you make him
Sure.
be present?
Sure. Thank you for your interesting talk and presentation. So what I got from your talk is that you believe that there is no deep connection between the second law of thermodynamics about the increase of entropy and the arrow of time. Now, my question is that, do you think that our impression about the arrow of time, the fact that we feel the arrow of time without knowing physics, do you think that that impression comes from the fact that we are macroscopic objects, we are macroscopic beings? Uh, for that, imagine that we were like particles in a cavity QED, where all the phenomena, all the processes are reversible. Could we say which arrow of, could we feel the arrow of time there? I think we couldn't. So do you
So let me first go back to the beginning of your question, if I can, because there's something I'm not sure I understood. You seem to say that I was saying that I don't think the direction of time has anything to do with entropy or with thermodynamics, but that's not what I think. And if I conveyed that impression, I did a bad job. I think talk about the directness of time. When I answered the first question, um, I said that there is a more fundamental metaphysical temporal structure, but it doesn't have any direction associated with it. And all of this sense of the directedness of time, it seems to me, does indeed come from the fundamental laws that account for thermodynamics. Things like the fact that there's a past hypothesis and no analogous future hypothesis. So, no, I think the direction of time has everything to do with entropy. And I agree with you that it's only at the level of the macroscopic that that a sort of pronounced direction of time imposes itself in any kind of vivid way, precisely because the direction of time is very intimately related to entropy.
I see. I see.
I don't know if that's answering your question, and I'm not sure if I understood you in the first place, but no, if I was giving the impression that I don't think the direction of time has to do with entropy, that's not what I think at all. I think it's all about entropy.
So then, do you think that at the microscopic level, at the level of tiny particles, we have both directions of time going?
Yeah, I think if you look at things on a macroscopic scale, it's impossible to tell whether you're being shown the movie forwards or backwards. And I mean, I don't know what it would mean. I don't know exactly how to think about, say, microscopic beings with consciousness, or how they would see the world. It seems an important feature of conscious activity that it has to be very physically complex. But if you ask me to try to imagine microscopic beings made of very small numbers of degrees of freedom with consciousness, yeah, I guess I would have to say I don't think they would be experience any directedness to time. Yes.
I see. So then can't we use them even if the particles are not conscious? Can we use them for signaling or for retrocausality or like
Oh, I see what you mean.
paradox?
So let's see. There isn't
if they can go backward.
questions. So there's a lot of questions to unpack there. One is, I don't think that talk about causation is a fundamental physical way of talking. I think that at the fundamental level, we have, the structure of space and time and the ontology of, say, particles, and we have laws of the motions of those particles. I think that talk about causation is much higher level talk than that. The only way I understand to talk about causation has to do with evaluating counterfactuals. A caused B means something like if A hadn't happened, B wouldn't have happened, and so on. And we don't get this kind of talk just from the fundamental laws. We need ways of evaluating these counterfactuals. We need a metric on distances between possible worlds. There's all kinds of stuff we need to do before we start to get to causal talk. So, so I see where you're going here, that if on the micro level there really isn't any direction of time, then why wouldn't it be the case on the micro level that we have backwards directed causes just as easily as we have forwards directed causes? And that could get us into certain paradoxes, bilking paradoxes and so on and so forth. So I see the thought there. No, I don't think that's actually going to be easy to work out. I think talk about causation and the direction in which causation is going is a very non-fundamental kind of talk. When you ask if on the fundamental level, if on the microscopic level there's no direction, then couldn't we have backwards causation there? You're taking it for granted that causation is a pretty fundamental way to talk. I don't think it turns out that way. I think to talk intelligibly about causation, you already have to be pretty far away from the fundamental level. You already have to be at a macro level. And at that point, thermodynamic considerations are already going to enter into things. So I think that the reason that we think causality is directed, that causes always come earlier than their effects, this is another piece of the world that's very closely tied up with thermodynamics and very closely tied up with the behaviors of macroscopic systems. And I think when you go to microscopic systems, it's not only talk about the direction of time that goes away, it's talk about the difference between cause and effect that goes away as well.
Okay, thank you very much. Let's have Bishar Atfar question. Please open his microphone.
Can I talk?
Yes, I can hear you.
Hello, Professor. How are you doing?
Good, thank you. How are you?
Thank you very much. As we can see in CMB, the variation in temperature is almost 1 in 100,000. Is that correct?
As far as I know, yes. Yes, it's something on that order. It's very small.
It's very close to the thermal equilibrium.
Right.
And the entropy is increasing. Yeah.
Indeed, what people have told me is that the variation in temperature in the cosmic microwave background is even smaller than what one would expect in thermal equilibrium, which is really mysterious. But anyway, I don't want to interrupt you. Go ahead. Yes.
Of course, of course. So as we go back in time, the entropy of the universe goes down. And
Yes.
when it's hit the CMB, it must be the lowest possible state. But it's seemingly its highest state of itself. Isn't it a contradiction or something?
So good. So first of all, I wouldn't say that as we go towards the origin of the universe, the entropy has to go to its lowest possible state. It starts out in some very, very low entropy state. Now, it's quite true that that the reason it's quite so. Imagine a puff of smoke, okay, which originally takes up a very, very small volume. You have a colorful puff of smoke, and it's in the middle. It's the puff of smoke forms a little sphere in the middle of a large empty box with transparent walls, so that we can see it. The puff of smoke may be at equilibrium for a gas confined to that volume. Okay, that is, the density may be uniform throughout that little sphere. The temperature may be uniform throughout that little sphere, so on and so forth. So the puff of smoke is at the highest entropy state that a puff of smoke that is confined to that spherical volume could be. Okay, but that doesn't mean that there isn't a way for this puff to increase its entropy. It can increase its entropy by spreading out, okay, by beginning to fill a larger volume. And that's how we're thinking of what the universe is doing in its early days. So you're absolutely right to say that the information we get from the cosmic microwave background is that at these early moments, the universe was in the highest entropy state that it could be in, given the constraint that it's still confined to this small region. Okay, but to say that it's the highest entropy state that it can be in, given that it's confined to this small region, isn't the same as saying that it's in the highest entropy state that it can be in, period. Okay, it has a way to increase its entropy. The puff of smoke has a way to increase its entropy by expanding its volume, and the same is true of the early universe. So I see why there's an apparent paradox there, but I don't think there actually is one.
So the answer is the volume.
Yes.
As you get a larger
Correct.
volume, you can.
Correct.
Okay,
Correct.
thank you very much. Thank you.
You're very welcome.
Thank you. In favor of organizers, let's have Sultan Manish question.
Sure.
Thank you for your amazing talk, Professor Albert. It was different, and I really like it. The thing that I understand the second law of thermodynamics works. I understand it in experience that the systems acts in a most probable way.
Right.
And if we want to change the direction of the second law of the thermodynamics, I just understand it that the system now acts as less probable way. Really acting in a less probable way mean that the direction of time changed.
I guess you could say that. I mean, if things consistently acted in an improbable way, there would be something wrong with the way we use the words probable and improbable, it seems to me. If the whole people sometimes wonder, for example, in the context of things like cosmological fine-tuning arguments, people say things like, there's a puzzle because the world as a whole the world as it presents itself to us is very, very improbable. Okay. I'm always puzzled when people talk like that. The first thing I want to ask them is, tell me, where did you get your ideas about what's probable or improbable? It must not have been by empirically investigating the world, okay? Because if you get your ideas about what's probable and improbable by empirically investigating the world, then it's just impossible by definition that the world as a whole could be highly improbable, okay?
Yes.
So they must have something, some other kind of consideration which led them to their convictions about what's probable and what's not probable. It must be something a priori. It must be something like principles of indifference or something like that. And I tend to be very distrustful of that kind of talk. I think claims about probability are like other scientific claims, claims that we believe for empirical reasons, not for a priori reasons or for any other kinds of reasons, but for ordinary scientific empirical reasons. So if you ask me to think about what the world would be like if everything was behaving very improbably, I start to get confused. Okay. Because I don't know what this word improbable means. Once again, if somebody asks me to imagine an entire universe in which everything is behaving very improbably, okay, things are happening which have very low probability, I get confused about what the word probability is supposed to mean. Okay. The first thing I'm going to ask this person is, I don't understand. What do we mean by probable and improbable, except the information about how things actually behave that we get by looking at the world?
Wow.
I don't know if this is just a way of evading your question, but I'm a little confused about the way that the question was put. If
No, no.
somebody says, "Oh, the whole world is behaving improbably," my first reaction is, God, I'm losing my grip then on what improbable is supposed to mean. Because the kind of grip that I have on what probable and improbable are supposed to mean makes it the case that it's impossible by definition that the whole world is behaving improbably. If it were, where did we get our ideas about what's probable?
I totally got your point. It just shake my thoughts. I haven't thought in that way. I had a little question. I think you said that you just think as time and entropy as two independent quantities, but entropy determines the direction of time.
Right.
What is time without direction?
Well,
What is the difference?
that's a really good question. Look, there's a paper that I very much admire about this from way back in the 1950s, by an American philosopher, D.C. Williams, called "The Myth of Passage." And what Williams suggests is something like this: Look, you start off with a four-dimensional manifold, okay? There's no distinction. You don't call one of the dimensions time. There's no distinction between these four directions. And this manifold is what people call decorated with properties. So you can say about this manifold, okay, at such and such a point in the four-dimensional manifold, there's a particle. At such and such another point in the four-dimensional manifold, there's a negative electric charge. At such and such another point in the manifold, there's a magnetic field, and so on. And all of these assignments of physical properties to points in this manifold are what are the entirety of the world, of the physical world. Okay?
Okay.
Then we can ask, look, it might be that we look at the distribution of these properties over the four-dimensional manifold, and we notice that there's a way of slicing the manifold up into three-dimensional slices, okay, in such a way that there turn out to be simple rules that connect the distribution of properties over one of those slices to the distribution of properties over others of those slices. Okay. If the world is, if the distribution of properties across the world is like that, okay, if we find that there are these simple rules that tell us what the distribution of properties is over one slice, given the distribution of properties over another slice, we say, oh, I see what's going on here. These rules are what we usually call dynamical laws, okay? And the direction along which these slices are separated from one another is the direction that we usually call time, okay?
Okay.
And the idea is that the fundamental difference between space and time is nothing more than that. So you have the following hierarchy. At the very metaphysical bottom of the world, there's just this four-dimensional manifold with these properties distributed over it. That's it. Okay. Go up one level, it turns out that you can find a way of slicing this manifold up so that you get these simple rules connecting different slices. Okay. And then you say, I'm going to call the direction that parameterizes these slices the time direction. Okay. Usually these rules work in both directions. Okay. That is, our fundamental physical theories are time reversal symmetric. That is, if I know the distribution over one slice, I can use these rules to figure out the distribution over another slice on one side of the original slice, and also in the same way for a third slice on the other side of the original slice. So there's no direction here yet. Okay.
Okay.
Then you go up one more level, okay, to macroscopic behaviors. Then you may get a direction, okay, associated with thermodynamic behavior. So the idea is time comes into the picture before a direction of time does, but at the very bottom of the whole picture, there's not even a distinction between time and space. There's just this four-dimensional manifold with properties distributed over it. Is that clear? I'm so sorry. I'm so sorry I didn't manage to get my camera working because I'm making all these gestures now and I realize that they're useless. But I hope that what I'm saying is understandable.
Yes, I tried to imagine that it was complete. And I get it. Thank you. Thank you very much.
Thank you.
Thank you very much. Please give me permission to have the last question.
Yes, of course.
Fatalian, I think. Please open.
Can you hear me?
Yeah.
Thank you very much for your nice presentation.
Thank you.
The thing which is important for me, you told that time is something more fundamental than the entropy
Right.
gradient. I want to ask if, in your view, if the directedness of time included the same. I mean, if the directedness of time is also more fundamental in your view.
No.
The gradient.
No. Here's what I think, and this connects to the answer I gave to the previous question. It seems to me that a distinction between time and space, okay, comes in at a more fundamental level than a directedness of time. Okay, that the minute you have dynamical laws, even if those dynamical laws are perfectly time reversal symmetric, okay, you already have a distinction between time and space. So you already have a notion of time. Okay. It's
Mhm.
not until you get further laws of macroscopic behavior where you distinguish between the two directions of time. So one could put it this way. You start out with this four-dimensional manifold, okay, which has
Mhm.
properties distributed over it. And in this four-dimensional manifold, there are no distinctions between time and space, no distinctions between any two directions in this four-dimensional manifold, nothing, okay? But then you get these physical properties distributed over the manifold. And those properties may pick out one of the axes as special, okay, without picking out a direction as special, okay. You may discover that on the microscopic level, there are simple rules that connect the distribution of properties um, um, on one slice with the distribution of properties on other slices, but they connect them in both directions symmetrically, so that at that stage, although a distinction emerges between space and time, okay, no
Mhm.
distinction emerges between the direction of time toward the future and the direction of time toward the past. Then, once you start to focus not just on microscopic phenomena, but on macroscopic phenomena, on thermodynamic sorts of phenomena, it's only then that you're going to get a distinction between the two directions along the time axis itself, the direction pointing toward the future and the direction pointing toward the past. So the short answer to your question is yes. I think there's a way one can talk very clearly about time and about a distinction between time and space that doesn't incorporate any distinction between one direction along the time axis and another direction along the time axis.
Mhm. Thank you for the description.
Thank you. Thank you for the question.
Thank you.
Okay. Professor Albert, do you have time to have one more question or?
Yes, of course.
Okay. Okay. Let's, Mr. Danish. To ask his question.
Hello.
Yes.
Uh, Let me, Professor. I want to change the our presentation, if you let me, from ontology, from entropy to the general relativity and the special relativity. Uh, as you know, general relativity and special relativity were presented by Einstein in 20th century. Our understanding of time have changed a lot.
Mhm.
The question right now is that as neuroscience approach and experiment about the time, they found that we can the same situation as Einstein presented with the neuroscience. I mean, experiment about electricity that gave to our brain. We have the same situation as we have in, for example, in special relativity. When you, for example, travel with the speed of the high speed. I
Mhm.
want to know that what's your idea about this approach in neuroscience? Thank you.
Can you tell me a little bit more about the approach in neuroscience that you have in mind? I mean, I certainly understand and agree with you that it seems now as if we're on the sort of on the cusp, on the eve of great discoveries in neuroscience that are going to change our understanding of how our minds work as profoundly as Einstein changed our understanding of how space and time work. But did you have some more detailed analogy in mind between what's going on, what happened in, say, the theory of relativity early in the 20th century, and what's going on in neuroscience now?
Let me give you an example. Uh, for example, if you travel by speed of light, okay,
Right.
the time it goes slower for you.
Right.
Okay, and neuroscience experiment today us that we have the same situation. For example, if you give, for example, a chemical substance or drug to someone, and also, or maybe give the electricity power to the brain someone, for example,
Right.
you can have the same situation as you have in, for example, in special relativity. You
I see. You
understand me?
mean time feels like it's going much more slowly.
Yeah,
Right.
yeah, exactly.
Right. So that's very interesting, and that's true. It's perfectly plausible that what you say is true. I'm not sure that I see. I mean, I'm not sure what to say. If the question is, do I see a really direct relationship between, between the
No,
kind of
no. Let me. Sorry, excuse me, interrupt you.
sure.
I want to say that understanding of time is just relies on our brain. You
Right.
know, if we have other brains, for example, or chimpanzee, or I don't know, any kind of the animal, you know, we
Yes.
might be having different understanding of time.
Oh, I
You
see.
know.
Sure. Sure. Oh, now I understand the question better.
Mhm.
Sure. I think that there's a very deep principle that as our sciences get more and more fundamental, are going to come up more and more often. Um, um, Let me describe it this way. Um, Here's something that seems to me to be an important difference between something that's a viable scientific theory, that's worth considering as a scientific theory, and something that merely succeeds as a skeptical scenario. Okay. In order for something to succeed as a skeptical scenario, all it needs to do is to say, look, here's a story about how the world could be that's consistent with all our observations. How can you be sure it isn't true? Okay. And
Mhm.
if there's no way that we can be sure it isn't true, then it succeeds as a skeptical scenario. But I think in order to be an interesting proposal for a scientific theory, it has to do more than that. Any interesting proposal for a scientific theory has to not only explain our empirical experience, okay, but
Mhm.
it has to have the feature that beings that could exist, okay, epistemic agents that could exist in the kind of universe that this theory describes, could come to have good reasons for believing that the theory is true. Okay.
Mhm.
So there is, in this way, a deep connection, I think, between what kind of fundamental laws we can entertain and what kinds of cognitive capacities, what kinds of physically embodied cognitive capacities those kinds of laws could support. Okay. Because one of the things we know about our world is that we exist and that we have the kinds of cognitive capacities that we do. Okay. And if I'm going to accept a certain scientific theory, it seems to me one of the things it needs to do for me is to explain how there could be, in the sort of world it describes, creatures like me who could, in principle, come to have good reasons for believing that that theory is true.
Okay, okay. Thank you. Thanks a lot, Professor.
You're very welcome.
Thank you.
Okay. Thank you very much. Professor Albert agreed to participate in this program and being patient to respond our questions.
Thank you so much for having me. I'm very glad to have been here, and I'm sorry again not to have been able to to show you all my face. But I'm very glad to have been here and very honored to have been invited.
No problem. It was an interesting talk, and thank you again. Have a nice day.
Thank you. You too.
Thank you, dear friends, gathering here, and I hope to have you all in tomorrow's talks too. Good afternoon and have a nice day.